platform, that is BYJU'S Exam Prep, everyone. And in the today's session, I have brought to you a very interesting session on structure analysis, movement distribution method. So we are going to be discussing about the movement distribution method in the today's session, everyone. So do join, everyone, and let me know if you are all excited to learn a new topic from structure analysis, everyone. So today we are going to be discussing about movement distribution method. Yes, welcome everyone. So if you are new to the channel, let me introduce myself, everyone. My name is Rohan Goyal, and I have a master's degree in structural engineering from IIC Bangalore. I have scored an All India rank of 96 in GATE 2020, and these are the subjects that I teach at BYJU'S Exam Prep, everyone. And a very important workshop is being conducted on our BYJU'S Exam Prep platform by Abhinav Negi sir on how to do step-by-step learning from beginner to become a topper. So this is going to be conducted on 30th of July, and that is today at 8 p.m. Actually, it has been already been conducted. So it has already been conducted. Okay. So now we are going to start with our movement distribution method. Okay. So in order to understand movement distribution method, first of all, let us understand what is carryover movement. What do you mean by carryover movement? So it is the movement developed at the one end due to an applied movement at the other end. What does it mean? Suppose if you have a beam in which the far end is fixed. Now let us understand. So what is carryover movement? So if you have a beam like this, in which the far end is fixed over here, and there is a, let us say, pinned support over here. Okay. Now if at this end, if you apply a moment of M, so due to this M moment applied over here, the beam would like to bend like this. The beam would like to bend like this. Yes, right? So over here, there is theta is equal to 0, and due to which a resisting movement will be developing over here at the fixed end, which is making this theta to be equal to 0 over here. Yes, so fixed end is going to provide a resisting movement which will not allow the member to rotate at that point. So this developed movement at this fixed end due to this applied movement at this pinned end is equal to m by 2 in the same direction like this. So if this is anti-clockwise, this is also going to be anti-clockwise over here. So this movement over here is referred to as the carryover movement due to the applied movement at this end. So let us say this is end number A and this is end number B. So if I write CAB, so it is defined as carryover movement at B due to applied load at A. So what is the carryover movement at B due to applied load at A? It is equal to, so carryover movement at B is anti-clockwise m by 2. So it is equal to m by 2. And this is applied movement is m. So this comes out to be equal to 0.5. So carryover factor comes out to be equal to 0.5. Clear, everyone? Any doubt? Hello everyone. Hello. Welcome, guys. Now, moving to the next concept is when the far end is hinge or a low roller. Now suppose if you have a simply supported beam like this. So now if in this beam, this is A and this is B. If you apply a movement at this location, So if we apply a moment at this location. Now, how the beam would like to bend? It will bend somewhat like this. And since this support over here is a pin support, there is no resistance to rotation. It is free to rotate. It is free to rotate. So what the moment developed over here is equal to 0. So there is no resistance over here. So 0 moment is going to develop at this location. So in this case, the carryover factor CAB will be equal to carryover moment at B, which is 0, due to applied moment at A, which is M. So it becomes equal to 0, everyone. Clear, everyone? If there is any doubt up to this point, you can ask me in the comment section. Yes, everyone. Clear? Now, when the far end is free, in this case, so basically it is a cantilever case. Now suppose if you have a cantilever beam in which one end is free and one end is fixed. Okay. So this is a free end over here. So this is A, this is B. In this case, when you apply a moment at A, the beam would like to bend in this direction. Due to this movement, it will like to bend like this, right? So due to which there is going to be a resisting movement over here whose magnitude is M. Now if you look over here, this movement is anti-clockwise, whereas this is clockwise. So the carryover factor CAB will be equal to the movement developed at this location is minus M, which means clockwise, okay, divided by M, which is anti-clockwise. So this comes out to be equal to -1. Any doubt? Any doubt to anyone, guys? Clear? So now you've understood what is carryover moment and what is carryover factor. Okay. Now from here you get to know if there is some movement applied at one end, what amount of the movement will be carried over forward to the next particular end, right? So from here you get to know about this thing. Now the next point is your stiffness factor and relative stiffness. So stiffness over here is referred to the rotational stiffness. So how much movement is required to produce a unit rotation at that particular point? So the movement required to produce a unit rotation at that point is referred to as the stiffness factor. Now, for example, if the far end is fixed like this, if the far end is fixed, right, if you apply a movement over here, now what is the amount of this movement applied over here due to which the rotation which is observed, this theta becomes equal to 1. So this value, if it is calculated, becomes equal to 4EI by L. So that means in this case the stiffness factor is 4EI by L. Okay. Next is here, if the now simultaneously the relative stiffness. Relative stiffness is something which is with respect to something else. Okay. Now the base with respect to which the relative stiffness is calculated is this one case. So for this case, the relative stiffness K is equal to I by L. Relative stiffness K is taken as I by L. It is taken as I by L, everyone. Now, with respect to this value, the relative stiffness of the other type of support condition is calculated, everyone. Now, suppose if the far end is hinged or a roller. In this particular case, now, what is the movement required to produce a unit rotation at this particular point? And this movement is equal to 3 EI by L. Okay, this is equal to 3 EI by L. Now in this case, the relative stiffness, if calculated, now for if in the case number 1, we have taken 4 EI by L equivalent to I by L in relative stiffness, right? Now if this is 4 EI by L is equal to I by L, then in our case number 2, our value is 3 EI by L. Now this will be equal to I by L divided by this L upon 4 EI multiplied by this, that is 3 EI by L. So EI by L and EI by L will cancel out, so this becomes equal to 3 by 4 I by L. So in this particular case, the relative stiffness comes out to be equal to 3 by 4 I by L with respect to the case number 1. Any doubt up to this point, guys? Any doubt up to this point, everyone? Any doubt to anyone, guys? Very good. Moving on to the next case, when the far end is free, that is our cantilever case. Now in the cantilever case, now in this case, the moment applied over here to produce a unit rotation is equal to, it is equal to so this is M upon this is EI by L. EI by L. All right. So when the far end is free, actually in this case we will not take this as fixed. Okay. So in the case of far end is free, let us take this as a pin. Okay, there is a reason behind it. Now, what is the movement required to produce a unit rotation? What is the movement required to produce a unit rotation? Which is, so this is, since it is free over here, so the movement required over here it will be equal to 0. So the stiffness factor will also be equal to 0 over here. Okay, the stiffness factor will also be equal to 0 in this case because this is free. So no, it is free to rotate. So there will be no resistance required over here. There will be no movement required over here. Now, what is this use of this relative stiffness? Using this relative stiffness, we are going to calculate what is the distribution factor. Distribution factor means if at a rigid joint, suppose there are some members meeting at a rigid joint. Like this, let us take an example over here. And this is free. And suppose, let us say you know the various values of the rigid joint. Let us say if this is I, all the members are of the same stiffness, EI is same. This is also EI. This is also EI, and this is also EI, this is also EI, okay, and this is 4 meter, this is 3 meter, this is also, let us say, 4 meter, okay, and this is again 3 meter. Now suppose a moment M is applied over here. Now, how much movement is resisted by each member over here depends upon its distribution factor. So, let us do the naming of all the joints over here. So, let us say this is A, this is B, this is C, this is D, and this is center is O. Okay. So, the distribution factor is defined as K upon summation of K for a particular member. Okay, let us draw. So we have members, K value, and corresponding to that distribution factor value. If I talk about member AO, In this, the far end is pinned in this case. So when the far end is pinned, the stiffness factor is 3 by 4 I by L. So I divided by L is how much? 4. So it comes out to be equal to 3 by 16 I. Okay. Let us keep it like this only. We will do the calculation later on. Alright. So 3 by 4 I by 4. Alright. Then member BO. Now in the member BO, the far end is fixed in this case. And when the far end is fixed in this case, the distribution factor is I by L. The stiffness factor is I by L. Then CO member, in this member also the far end is fixed, so the stiffness factor is again I by L. And lastly, when the DO member, the far end is free, in this case the distribution factor is, the stiffness factor is 0. And what is the value of summation of all this? If you do the addition of all these, it will come out to be equal to 4. So 4 by 3. So if, let me do the calculation, you can calculate side by side. Tell me what is the final value you are getting over here. So you are going to get 37 upon 48 I. So the distribution factor of member AO will be equal to this divided by this. So it is going to be equal to 3I by 16 divided by 37I by 48, which is equal to how much? Zero point, or yeah, 0.243. Similarly, this will be equal to I by 3 divided by 37 by 48I, which is equal to 0.432, and this will be I by 4 divided by 37 I by 48, which is equal to 0.324, and this will be equal to 0. So these are the distribution factor. Now just do the summation of all the distribution factor over here. How much you are getting? You will get 0.999. So you can round off any one of the values. Okay, let us round off this 0.244, let us say. So it will come out to be equal to 1. So the summation of the distribution factor at a joint is always equal to 1. Now what does it tell you? That out of this total moment M, over here, 0.244 M is going to be resisted by AO member, 0.432 M is going to be resisted by BO member, 0.324 M is going to be resisted by CO member, and 0 moment is going to be resisted by DO member. Any doubt up to this point, anyone? Yes, kindly comment in the chat section and let me know. Any doubt to anyone, guys, up to this point? Yes, everyone. Now we will understand the next concept of fixed end movements. Okay. Now what are the fixed end movements? Fixed end movements are the movements which are going to develop at the fixed ends due to the applied load along the span. So if suppose if you have a fixed beam which is subjected to a point load at the midspan, okay, L by 2, L by 2. In this case, let us, if this is A, this is B. The fixed end moments are given by, so let me draw all the types of cases. Okay, so these are all your cases, right? Okay, so in this case, the fixed end moments which are developed in resistance of this given load over here is fixed end moment AB. That means A to B we are taking, this joint we are talking about, in the span AB at joint A we are talking about, is equal to WL by 8. And similarly over here, see, whenever we are calculating the fixed end moments, always take sign convention. And the sign convention for the fixed end moments is to take clockwise movements as positive and anti-clockwise movements as negative. All right, so this is anti-clockwise, so this is going to be taken as negative over here. Since this is anti-clockwise, this is going to be taken as negative, minus WL by 8, and this is clockwise, the fixed end movement BA will be taken as positive, that is WL by 8. Now similarly over here, the fixed end movement, this is A, this is B. MFAB is equal to minus WL square by 12 at this point, and over here the movement will be WL square by 12 plus, since it is clockwise. And lastly, in this particular case, the fixed end movement, this is A, this is B. Okay, fixed end movement AB is equal to W B square A upon L square, and since this is anti-clockwise, it is going to be negative, and the fixed end movement BA is equal to W A square B upon L square. Okay, so like this you can find out the fixed end movements. Now let us use all these concepts in a problem, and you will understand how to use movement distribution method and all the concepts that we have studied up till now in our problems. So let us do one problem now, right? So the problem is this one. So you have a beam which is, let us say, a continuous beam you have, which is subjected to UDL over here and a point load over here at the midspan. The magnitude of the UDL is 12 kilonewton per meter. Okay, and this value is 8 kilonewton. Okay, this is 8 meters and this is also 8 meters. So this is 4 meter and this is also 4 meter. And you are asked to draw SFD and BMD for this problem over here. So you have to draw the shear force diagram and the bending moment diagram for this problem over here. Now in this we are going to use various steps. Okay, so the step number 1 is going to be very simple to find out the fixed end moments. fixed end moments. So in order to find out fixed end moments, we are going to find out fixed end moments for each span. So AB span AB, right? So we are going to make the ends fixed in the span AB in order to find the fixed end moments, which is subjected to a UDL of 12 kilonewton per meter, 8 meter of length. This is A, this is B. So in this case over here, the fixed end moments will be equal to WL square by 8, 12. So anti-clockwise, so minus. So this is going to be equal to minus WL square by 12, which is equal to minus W is how much? 12. Length is 8 square by 12. So this cancels out and this becomes equal to minus 64 kilonewton meter. Yes, everyone. So this becomes minus 64 kilonewton meter. And similarly, the fixed end moments at this point MFBA will be equal to, since this is clockwise, this is going to be positive, WL square by 12, which is equal to 12 into 8 square by 12, which is again 64 kilonewton meter. Similarly, find out for the span BC. So you will make the ends as fixed for the span BC. Okay, and it is subjected to a point load at this location whose value is 8 kilonewton. Okay, so the fixed end moments MFBC will be equal to WL by 8 minus WL by 8, which is equal to minus 8 into 8 by 8, which is equal to minus 8 kilonewton meter. Right, everyone? Yes, guys. And similarly, the fixed end moment MFCB will be equal to WL by 8, which is equal to 8 into 8 by 8, which is equal to 8 kilonewton meter. Any doubt, guys? Any doubt up to this point? So we have calculated the fixed end moments now. Now in the step number 2, we are going to find out the distribution factors. So let me do the step number 2 over here. Okay, so some points that I would like to note down over here. Step number 2 for distribution factor. Now if I talk about joint A and joint C, if I talk about joint A and joint C, whatever movement you are going to apply at the joint A, don't you think the whole movement is going to be transmitted only in the one span over here, because there is only one span in this case. If you apply a movement M in this joint A, the whole movement M is going to be taken care by the AB span. And if you apply a movement M in the joint C, the whole movement is going to be taken care by the BC span. So the distribution factor for joint A and joint C is equal to 1 only, right? So this is equal to 1 for these two span. Now now we have to find out the distribution factor at joint B. So find joint B. It is to be calculated now. In order to find this, all right, let me draw the diagram once again. So this was our problem, right? All right. Right. So let us find the distribution factor at joint B. So in our joint B, okay, we have our member, our stiffness factor, and then final distribution factor. So at joint B, we have member BA and BC. Now in the member BA, the far end is pinned. So when the far end is pinned, the distribution factor is 3 by 4 I by L. 3 by 4 I by length is 8 meters. And similarly for the member BC, again the far end is pinned. So again it is going to be 3 by 4 I by L. So the summation of distribution factor will be equal to 2 times 3 by 4 I by L, right? So this divided by this will be nothing but 1 by 2, which is equal to 0.5, and this will also be 0.5. What does it mean is, whatever moment is applied at the joint B is going to be equally distributed between the two members. Whatever movement is going to be applied at the joint B is going to be equally distributed in the two members. If it is applied 10, it is going to be 5 in each case. If it is 20, then 10 each case. Clear, everyone? Right? Now we will go to the next step, in which we are going to conduct the movement distribution. Step number 3, movement distribution method. So in this, we have our joint, joint A, joint B, and joint C. Okay. At the joint A, the distribution factor is 1. Joint C is also 1. And the joint B is 0.5 on each side. Fixed end movements. What are the fixed end movements? At MFAB is minus 64. This is plus 64. This is BC. MFBC is minus 8. And this is plus 8. Right? Now, first of all, since we know A and C are pin supports, so there is zero movement at these two supports. So since there is a zero movement at these two supports, we have to release these supports. So release A and C. So to make it 0, we will add plus 64 over here and minus 8 over here. So I have applied an external movement over here of plus 64 and minus 8 at these two locations to make the movement at these two locations equal to 0. Now if the applied movement at A point is 64, so what is the carryover movement at B support? Now, right now the B support is a fixed support because it is as per the fixed end movements. So right now, as per the fixed end movement, this is fixed. So when the far end is fixed, the carryover movement is 64 by 2, that is M by 2. So plus 32 over here. And similarly, the carryover movement of this will be minus 4, right? So what is the net movements? Net fixed end movements. So net will be equal to 0. This will become out to be 64 plus 32, that is 96. plus 96, and this will become minus minus 12. Okay, and this will again become equal to 0. Any doubt up to this point? Any doubt? Okay, clear guys? Now what is, now we have to release the joint B also. Now this joint B is not a fixed, this is a continuous support. So we have to release in such a way that the movement comes out to be is weightedly distributed in both the spans. So what is the difference over here? 96 minus 12 is 84. So this 84 will be equally distributed on both the directions. So minus 84 by 2, that is minus 42 over here and minus 42 over here. Okay, so what is the carryover moment? When the far end is hinged, now carryover moment in this case will be equal to 0, because now the far end is hinged in this case. So the final fixed end movements, final movements will be equal to 0. This will become 54. Again minus 54 and 0. Clear everyone? Now you know the movements at each and every joint. Now you can draw the free body diagrams. Now you can find out the support reactions. Now step number what is the step? 4. Support reactions. Now this is my span AB, which is subjected to a UDL of 12 kilonewton per meter. Okay, so all right, okay, this is 8 meters and a movement of plus 54. So this is plus 54 means clockwise. 54 kilonewton meter is going to be acting over here, and in the member BC load of 8 kilonewton is acting over here. This span is 8 meters, and over here anti-clockwise movement is over here of 54 kilonewton. Now what are the support reactions? Now the support reactions due to applied load, so this is joint A, this is joint B, and this is joint C. Okay, now the movements at the joint A due to the applied load, that is this UDL, will be WL by 2. So 12 into 8 by 2, which is in the upward direction. Clear? So, and at the joint B will also be again equal to 12 into 8 by 2, which is also in the upward direction. Due to, in this case, due to this 8 kilonewton, so it is going to be 8 by 2 in the upward direction, and at the joint C also 8 by 2 in the upward direction. So this is due to the applied loads. Now due to movements, over here there is a clockwise movement. So there is going to be an anti-clockwise couple. At A it is going to be M by L in the downward direction. So 54 by 8 in the downward direction. And over here it is going to be 54 by 8 in the upward direction. And similarly now over here it is anti-clockwise, so the resisting couple will be clockwise, so it is going to be 54/8 in the upward direction, and here it is going to be 54/8 in the downward direction. Okay, clear? All right, so what are the final movements that you are getting? So take upward as positive, downward as negative. So final reactions. The final reactions are going to be, this is going to come out to be equal to upward take as positive, downward take as negative. So everywhere, wherever is upward, take positive, downward negative. So this will come out to be equal to plus 41.25 kilonewton. Add all this. $65.5 kilonewton, and this one 10.75 kilonewton. Just check once again. All right. So mistake is there. One second. And this much is right, no problem over here. WL by 2, WL by 2, 8 by 2, 8 by 2, 54 by 8, 54 by 8, 54 by 8, no problem over here. Then why is it so having an issue? There should not be an issue then. Actually, the summation of vertical forces is not coming out to be equal to 0. There is some issue over here. WL by 2 for 48 minus 54 by 8. Okay, this is 63.5, I guess. 24 into 4 plus 8 by 2. No, it is 65.5 only. 4 minus. Okay, this is minus. Okay, this is wrong. This is wrong over here. This is minus 2.75 kilonewton. So if you add all these values, then you will get 104, which is equal to this. Now it is okay. Now if you draw the final diagram to draw the shear force and bending moment diagram. Now let us draw the final diagram. Over here the reaction is 41.25. This is subjected to a UDL. Over here the reaction is 65.5. A point load over here of 8, and over here the reaction is in the downward direction, that is 2.75. Now let us draw the shear force diagram. Okay, so the shear force diagram over here plus 41.25. Then there is a UDL, so inclined straight line in the downward direction, and this will become out to be equal to 41.25 minus 12 into 8, which is minus 54.75. Then there is plus 65.5. So it will go up with a value of 65. So plus 65.5. So this will become 10.75. Then it will be straight. Then minus 8. Minus 8 will become 2.75. So again it will become 0. Okay. Sorry. Minus 8, it will become 2.75, and now it will become 0, like this. So plus, minus, plus. All right. Now, if you draw the bending moment diagram, your bending moment diagram will be somewhat like this. So it will be like this. Okay. And then it will be straight line reaching to a maximum value over here, and then 0. So plus, minus, plus. This will be your bending moment diagram. This is your shear force diagram. Okay, so that's all for the session, everyone. Is there any doubt at the end? You can ask me, guys. Is it clear to you all how to find out the shear force and bending moment diagram using moment distribution method, everyone? Is it clear to everyone? So thank you, everyone. Take care. See you in the next session, guys. Bye, everyone.